Okay, so one of the things I get asked an awful lot when I'm teaching astronomy and astrophysics is how CCD images taken at the telescope or at the spectrograph are properly calibrated using biases, darks, and flat fields, and why each one of these frames is necessary to do the job properly. So I'm going to try to answer many of those questions. This is certainly not going to be exhaustive because I don't have the ability to do the kind of math that is necessary here as quickly as humanly possible, but I'm going to try. So here's what's going on. You take a bunch of images, and we'll start with frames that we know. The light frame. The light frame is the picture that you take of your target. So maybe you're imaging a variable star or a galaxy or a planet or something, and you take a light frame and you take it for some quantity of time. We'll call that an integration time. And this contains the data that you're interested in keeping, but it also contains a bunch of information you don't want, noticeably unwanted signals and unwanted noise. And the process of calibration, at least that term is used by most softwares. The process of dealing with biases, flats, and darks to reduce the noise and unwanted signals in your light frame is the process we'll call calibration. And that's what we're trying to do here in this talk here. Dark frames are as they sound. They're literally an image of darkness, an integration of darkness for some quantity of time. And they're also taken at the same temperature as your light frame, if at all possible. Not all CCD cameras have temperature control. Most of them do these days. I would recommend that you operate as cold as possible because that reduces the black body radiation that causes an awful lot of the dark signal that you don't want, the thermal noise that you're unwanted here. So if you're going to make any changes to your world by taking CCD images, light frames, the number one method of reducing your noise is to subtract the dark noise. There's the bias frame. The bias frame is a 0-second integration. You're like, what? How do you take an exposure that's 0 seconds long? Well, what happens is the CCD camera is read out very quickly, and then that information is literally deleted, and then it's read out again as soon as possible. And it's the second readout that you're interested in. It's called the bias frame. The bias frame is literally the combination of signal and noise that comes from the process of reading the actual chip out into memory. You guys are all probably really familiar with things like light bulbs. Light bulbs have electrons flowing through them, and when electrons flow through them, the filament in the light bulb heats up. And in the case of a light bulb, it heats up to the point where it gives off wavelengths of photons, visible light, that we can see. The bias frame is kind of similar to that. Electrons are being shifted. The charges from each of the pixels is being shifted to other pixels, and it's being read out in a readout register, and all that information from the readout register is going through an amplifier circuit, and then from the amplifier circuit through to an analog to digital converter, where it's converted to some value between 0 for black and typically 2 to the 16th power, 655, 35, which would be a pure white, would be a full well capacity for the CCD chip. Not all CCD cameras are 16-bit cameras, just pointing that out. Some of the older ones, particularly the tracking ones, were 8-bit, and some are higher than 16-bit. So the last one is the flat field. The flat field is an image ideally taken of an equally illuminated surface that is reflecting equal amounts of photons across all wavelengths that your CCD camera is sensitive to. So typically from ultraviolet through to infrared. There are limits. The quantum efficiency of your chip determines how far into the ultraviolet and how far into the infrared you'll be able to sense photons. But I'm not going to get into QE discussions here. Suffice to say that the flat field is taken to eliminate issues having to do with changes in sensitivity across the surface of your CCD chip. Chips are not equally thick. Some pixels can contain slightly more full well values of charge than others. Therefore, some areas are more sensitive to picking up photons than others. So if you take a picture of an illuminated white frame, the ideal perfect CCD would give you back a perfectly white image. But the truth is far from that. Some pixels will always record more light than others, so you may have more sensitive sections of the CCD chip than others. You may also have hair or dust or fingerprints, forbid, or ice or vignetting from your optical system that causes the CCD image to pick up light with different levels of sensitivity across the entire surface. And that's what the flat field is trying to do. Now, every light frame contains dark noise. Because the dark is a collection of thermal signal and noise that the chip is picking up because it is its own black body radiator. That's why we chill it. The light frame is also collecting dark noise as it is integrating. So if you take a 1 minute exposure of light, you're going to get 1 minute of dark exposure added to that, and that is easy enough to subtract. But it is also important to note that both the light frame and the dark frame also contain bias readout noise. So before you can subtract dark noise from the light frame, you've got to subtract bias noise from both the lights and the darks. And there's something else going on here too. So suppose I have a light frame here, which is a I'm gonna cheat. This is 1 pixel, okay? Maybe your light frame has a pixel value of 1000, which is not all that bright, by the way. And then you take a bias frame, which is, as we recall, the bias frame is a 0-second readout, and let's just suppose that it's got a 10 pixel value. You're like, okay, how do we get the bias noise away from the light? Well, you just subtract it. That's easy, right? So we combine these two, and you end up with a new pixel that is 1000 minus 10, which is 990. You've gotten rid of the bias noise, and life is good. You're like, okay, that's cool. Then you have a dark frame. And remember, the dark and the bias and the flats are all taken at the same temperature. None of this works unless they're all at the same temperature. Maybe -30, -40. I'll talk about temperature in a minute. This dark frame of yours results in a value of, let's bring it up there. Let's make it about 2000. But I want to tell you that the time of the dark frame is 3 minutes. Now let's make it 2 minutes. No. Let's make it 4 minutes. It's a 4-minute integration. And the light frame here, the time for the light frame is a 1-minute integration. And the bias, of course, is a 0 minutes or 0-second integration. You're like, okay, that's great. The reason people take dark frames that are longer than the typical light exposure is because the longer you take the integration for, the better your average values will be, particularly if you've got problems with cosmic ray strikes. Maybe you've got some other things that are inconsistent in your environment, like fans running in the background with a back EMF that go into your CCD images, which, by the way, is horrible. Take many long darks as possible. Mine are typically 300 to 500 seconds long, and I'll take several hours worth and average them all together, all at the same temperature. The dark also contains, of course, a bias frame. So what you do is you take your bias frame and your dark frame, and you subtract the bias from the dark, and you get a corrected dark here, which in this case is going to be 1990. We're just subtracting the 10 of the bias readout. So now the bias noise is gone from the dark. But you remember, this is still a 4-minute value. We then divide it by 4, and I'm just going to put divide by 4 minutes to bring it back to the amount of time of the light frame, and you end up with a new value here. So if we take 1990 and we take it and divide it by 4, you're going to end up with 497.5 or something like that. Let me do this on a calculator and at least give you some accuracy. As I said, I'm not the best at doing math on the fly, which is kind of annoying. So let's see, 1990, enter 4 divided by, 497.5. So here's our new pixel value. So in the course of 1 minute, you've gained a readout of 497.5 of thermal noise. This is your corrected dark. So we need to take the new light and we need to combine it with subtraction of that dark value there, and we end up with a new light frame that is 990, and it's subtracting 497.5 from it to give you a new light frame of 492.5. And yeah, it's okay to work in non-integer values. By the time you're done, you'll have real values, and if you're not careful, we'll even get some negative values in pixel values if we're not careful. So this is the new light, the new improved light, which has had both bias frame and dark noise subtracted from it. Again, a simple thing. Normally, for bias frames, we'll take 10 to 20 of these and average them together. And same for darks. We'll take, I'll take 10 to 50 of these and average them together to get a master dark and a master bias. The flat field now comes into play. It's like, how does the flat field play into this? We take, again, we'll take flats. And let's pretend that its value is going to be huge. It's going to be a large value. So here's a flat, and it's an average of like 50 or 60 flats, all taken through the same filter, at the same temperature, and at the same rotation, and the same focal point as your light, which makes flat fields a real pain. You should take flats as often as possible, which may not be easy, but we can talk about that some other time. Suppose you have a flat value that's 22,500. And notice it's high. You're aiming at a fairly bright object. Sometimes it's a specially painted board on the wall of your observatory dome. Sometimes it's at the blue sky. But it should be something that's equally illuminated as much as humanly possible. Well, we have to subtract the bias, right? Because it contains a bias. So our bias was a value of 10. So we're now down to 22,490. And then, oh yeah, the flat was taken for some time period. The time is 1 second, which equals 1/60th of a minute. And you're like, okay, that's sneaky, Blackwell. Flats can be any length of time. I recommend longer flats. 1 to 5 seconds are good. Anything under a second is risky because you get into shutter effect problems. So there you go. You got 1 second flats. They've been averaged together after you've got all your biases subtracted from it, but it's still a 60th of a minute. It's not a minute long, but it does contain dark noise. So now you have to subtract darks from that. So you take the dark, which has already had its bias removed, right? Your 4 minute dark subtracted. This is a 1 minute dark up here. You take it, you take your dark and you divide it by, this is divided by 4. So that's a 1 minute dark. We need to divide it by 60 to get it down to 1 second. So here's your dark. 497.5 divided by 60 gives you a value of dark for a 1 second exposure of 8.29 and some change. So you subtract your dark and you end up with a new value here for your flat of 22,490. 22,490 minus 8.29, which yields 22,481 and some change, 0.7. Okay, there's your 1 second flat. You're like, great, what do I do with it? Well, in the real world, you'd have multiple flats and you'd have multiple pixels in your camera. So suppose your camera looks like this and it has 4 pixels and you have flat A, B, C, and D. What you would do is you take A plus B plus C plus D and you divide it by the number of pixels you have, which is 4, to get an average flat value. Average flat pixel value. Okay, and that was easy, right? So now you have a flat value, and it's called your master flat. And now you have your average flat pixel value, which is a single value. It's a number, all right? What you then do is you go up to your new light, and for each and every single pixel, you multiply by the average flat value, by the average flat pixel value, and then you divide by each master flat pixel value. And what you're doing here is you're generating a ratio and you're multiplying it times the new light, and that changes the value of the light. So if the pixel was not picking up as much light as it should, it makes it brighter. It increases its value. And if it was too bright, it brings it down again closer to the average master flat value. So basically you're making a ratio and you're multiplying it times the new light, and then you end up with a finished CCD calibrated image. This is it, calibrated, yay. And life is good. Your calibrated image. And that's it, fini. Done. Hopefully that makes some sense, and we'll go from there.